Talk this afternoon. So it's a pleasure to introduce Arup Chattopadhyay from IIT Guwahati, and his talk is entitled Kopyenko-Neidhart Trace Formulas.
Okay, thanks to the organizers, mainly Joydev, so for giving me an opportunity to speak here, especially on the occasions of my advisor's 75th birthday. Okay, I guess I am his last PhD student officially. Okay, though Paramita is here. Okay, so the title of my talk is Kopyenko-Neidhart Trace Formulae. So this is actually a current interest of Professor Sinha. In fact, we are working together on a different problem in this direction. Maybe at the end, if time permits, I will talk about a little bit about that. Okay, so this is a ongoing work with my students Soma and Chandan. Okay. Okay, happy birthday, sir. Okay, I copied this photo from Joydev's website. Okay. Okay, so this is the overview of my talk. So first few minutes, I will talk about a little bit about the history of the problem. So in fact, I will talk about Crane's trace formula and Kopyenko trace formula, both in self-adjoint as well as unitary operators. And then our main aim is to revisit Kopyenko-Neidhart trace formula. In fact, we gave an alternative proof of it via finite dimensional approximation. So it has three major steps. First, we need to calculate the formula in finite dimension explicitly. Second step, we need to reduce our problem into finite dimensional case using Weil-von-Neumann construction. And at the end, I will show you the existence of shift function in infinite dimensional through some limiting procedure. Okay? And then we have some references. Okay. Actually, the notion of spectral shift function that is originated from the work of Lipschitz, and then first mathematical formulation of this object due to M.G. Crane. So that is why Crane's trace formula sometimes known as Lipschitz-Crane's trace formula. Okay? So what Crane's trace formula says is the following. So you start with a single self-adjoint operator, say H0, okay, could be unbounded. Then you perturb it, perturbed by nice class of operator. Nice means what? So I am considering this V is self-adjoint and coming from trace class operator, say B1. So this is another operator, so let it be H, could be unbounded. So that means I am dealing with two operators, H and H0. So this H0 is called the initial operator and this is the final operator. So that their difference is trace class. Then Crane proved that for nice class of function phi h minus phi h0, that is also trace class. Not only that, if I take the trace of this expression phi h minus phi h0, that can be written in terms of the integral representation along with the first derivative of phi with some function xi, then d lambda. But this function xi actually depends only on the initial operator and final operator, not on the function. And this function is called the Crane spectral shift function or first order spectral shift function. Okay? So this is for the self-adjoint case. Of course, the original proof of Crane, so I should write this is first order. Now the original proof of Crane uses analytic function theory. I am not going to discuss about that part, but many authors give an alternative proof of this formula. For example, in 90s, I forgot the exact year, Voiculescu approached this formula from different point of view. That means what? He actually reduced this problem into a finite dimensional case, and then in finite dimension he explicitly calculate the trace of this object. In other words, explicitly give an expression of the xi function, and then finally to give the existence of shift function in infinite dimension he used some kind of limiting procedure. So that is the first proof by Voiculescu, finite dimensional approximation. Of course, Voiculescu did for bounded self-adjoint operator. Then Sinha and Mohapatra, they extended Voiculescu's technique to unbounded self-adjoint operator case. That is for the Crane's test formula for self-adjoint. Okay. So now, what about the unitary case? So that means I change my initial and final operator by unitary operator. So that means start with a unitary operator U naught. Then you perturb by say some trace class operator. So let's say this be another operator. Okay. So that means in other words, well, start with two unitary operators so that their difference is trace class. Then Crane actually proved similar kind of formula for the unitary setting as well. So he proved that trace of phi u minus phi u naught, this thing can be represented as integration over circle phi prime of z eta z and then dmz. What is dmz? This is actually normalized Lebesgue measure on the circle. But the difference between unitary case and the self-adjoint case, in self-adjoint case the function xi is actually unique, but unitary case this is unique up to an additive constant. Well, of course this proof is functional analytic. Later on, once again Sinha and Mohapatra, they proved this formula again via finite dimensional approximation. So that's all about first order test formula for self-adjoint case as well as unitary case. Okay, now let's go to the second order case. Okay, so therefore the natural question is, can we extend this first order test formula to the second order? That means what? Okay, so Copeland actually extended Crane's test formula to the next order. What he did is the following. Again, he start with initial operator H naught, then he perturbed not trace class operator but by Hilbert-Smith operator. So that means you have two operators H and H naught, their difference is Hilbert-Smith. Then you can easily check that this difference, if I consider, that needs to be in trace class. Okay? So instead he considered subtract one more object which is actually Fetcher derivative of phi at H naught acting on B, and consider this expression. For nice class of function, this expression is actually trace class, and if I take the trace, he showed that it has a nice integral representation of the second derivative of phi. So that means this is over R phi double prime lambda eta lambda d lambda, and this function eta is actually called the Copeland spectral shift function. Okay. Well, once again, this Copeland test formula, many authors gave an alternative proof of it. For example, I think 2007, Gestesi, Pusnitsky and Simon, they gave an alternative proof. Later on, myself and Sinha, we also gave an alternative proof via final dimensional approximation. And well, I should mention that I think in 2009, Dykema and Skripka, they found a gap in the original proof of Copeland. Okay. But later, this group, Anna Skripka, Denis Potapov and Fedor Shukochev, they actually removed that gap, and they not only proved the Copeland test formula, they actually give an existence of higher order spectral shift. So not only second order, but also for any arbitrary order. So actually that was a conjecture of Copeland. They recently solved it. Not recently, I think 2013 they solved it. Okay. So this is for the self-adjoint case, second order. So natural question is, what will be the Copeland test formula for the unitary setting? And once again, Neidhart came into the picture. So Neidhart extended Copeland test formula for the unitary case. So that means, so he considered two unitary operators U naught, their difference is Hilbert-Smith, and then Neidhart proved that, consider this expression for nice class of function phi u minus phi u naught, then the dt of phi of okay. So I should say that if I take two unitary operators, their difference is Hilbert-Smith, then there exists a self-adjoint Hilbert-Smith operator such that U is equal to, that you can prove it. Okay? Then you consider this path. And for this path, so look at here, if I consider this path, this is also unitary operator. So that means Neidhart proved this formula for the unitary path. And what is this formula? So trace is nothing but integration over circle So once again, this unitary case, second order spectral shift function, that is also not unique. It is unique up to an additive constant. Okay. So our aim in this talk is to revisit this formula and give an alternative proof using finite dimensional approximation, like the way Voiculescu did for the first order case in self-adjoint setting, or Sinha and Mohapatra, they also did for unbounded case and also unitary case as well. Okay. Well, so that is Crane's test formula. So this is called Crane class. For this class of function, Crane showed that if I take two operator, H and H naught could be unbounded, and their difference is test class. So this difference also test class, and trace has this kind of representation, and this function xi is called the Crane's spectral shift function, where A and A is like this, B is like that. A could be minus infinity and B could be plus infinity. Well, so this is the history. So the function xi is called the Crane's spectral shift functions. Original proof uses analytic function theory, and this later, I think 1985, Voiculescu actually approached this formula from different point of view. In other words, he expressed this trace like limit of this Phn. What is Hn? Hn and H0 sub n. This is actually a matrix or self-adjoint matrix. So he approximated in some sense, and then since now I am in finite dimensional setting, you can write explicitly the xi functions, and then you have to give some kind of justification to give the existence of shift function in the infinite dimensional case. Voiculescu did it. Okay. Later, Mohapatra and Sinha, they extended Voiculescu's method for unbounded self-adjoint case. Okay. This is the first order test formula corresponding to unitary operators. So that means start with two unitary operator, difference test class, then trace has this kind of expression. So this is actually once again due to Crane, and of course another proof or alternative proof by Sinha and Mohapatra they have given. Well, so this is little bit about the history. So Copeland, this is the original proof. So then, well, Copeland actually extended. So as I already said that this difference did not meet test class if I take the difference is B2. So therefore you have to consider this kind of expression, and once I have that, then this is the corresponding Copeland test formula. So this is Ph minus Ph naught minus this is the Gauss derivative. This has the integral representation in terms of the second derivative of y, and this function eta is called the Copeland spectral shift function. Okay. Well, so that's 2007. Kestesi, Pushnitz, and Simon, they gave an alternative proof, and this is Dykema and Skripka. They found a gap. Later on, this Potapov, Skripka, and Shukochev, they actually removed that gap and give the existence of higher order spectral shift. And at the same time, myself and Sinha, we also gave an alternative proof using finite dimensional approximation. Okay, so a similar kind of problem for unitary case considered by Neidhart, and Neidhart assumed that okay, if you have two unitary operators, so that their difference is B2, then there exists a self-adjoint operator A which is also B2, and this trace, if I consider this expression, if I calculate the trace, it has the representation in terms of the second derivative of phi with some function eta, and this eta actually unique up to an additive constant. Okay. Well, so one more history is that Paler actually extended this Copeland-Cohen-Neidert formula to the Bishop class, and 2012 actually Potapam and Sukochev, they actually prove Copeland-Cohen-Neidert formula, but instead of going through this path like e to the ISA u naught, they consider linear path. So that means they consider this path. For this kind of path, they actually proved similar kind of formula. Of course, that was a question posed by Gestesi, Kuznetsky, and Simon. Okay. So that's all about a little bit of history of this problem. Now, this is our contribution, is that we want to give an alternative proof via finite dimensional approximation, and it has three major steps. First of all, I need to get an explicit expression. Of course, I am doing everything for this unitary case, unitary path. So I need this expression, trace, that means I need to get this expression for the finite dimensional case. In other words, I need an explicit expression of eta function for the finite dimensional case. That is the first step. Second step, using Weil-Fornamen construction, I need to reduce my problem into finite dimensional setting. And then finally, I have to give the existence of shift function using some limiting procedure. Okay, so this is kind of known theorem. So if you have two unitary operators, so that their difference is B2, then there exists a self-adjoint operator which is also in B2 such that U has this kind of representation. Well, proof is, I am not going to the details of this proof. What you do, consider this operator, this is also unitary operator. From that, you can give the existence of self-adjoint operator A, and you have to use this estimate. Using this estimate, you will be able to prove that A is also B2. Okay, so this is the first theorem. Actually, the expression, I want explicit expression of Copeland spectral shift function for the unitary case. So this is the expression in finite dimension. So of course, these two things, actually this is also true for infinite dimension. You don't have to assume that we are in finite dimension. So what is this? This is the corresponding Fetcher derivative, and you have to show that if I consider this expression, this should be in test class, and this is the actually major ingredient for the finite dimensional case. So that means I need to calculate this trace and actually the expression of eta, and we have calculated it. Actually, we got that eta has this kind of expression. Eta is nothing but trace of E naught is nothing but the spectral family corresponding to the initial operator, and ES is nothing but the spectral family corresponding to US. What is US? US is nothing but so this is US, e to the ISA U naught. Okay, so proof is just calculate the derivative as the usual sense, then you can see that this Fetcher derivative is nothing but this one. And finally, if I calculate this object Pu minus Pu naught dds of Pus, of course everything I am doing for the complex polynomial. So in fact, if you take the monomial, it is enough to do all kind of calculation. So therefore, this difference, and I know this expression of this one, then you just write everything in telescopic sum and order nicely, then you have final this kind of expression. And look at this, since U minus U naught is B2, so therefore this is B2, A is Hilbert-Smith, this is B2, so product is test class. Similarly, this is also test class, so therefore this object I have considered this is actually a test class operator. Well, now if you restrict yourself in finite dimensional case, so for this monomial, you can calculate this expression of trace. So what you have to do, so you have to use spectral theorem for unitary operators, and you have to do integration by parts. And you have just noticed that the boundary term vanishes. If you do if you perform all kind of calculation, then you will be able to end up with this kind of expression. So this is from 0 to 2 pi d2 d phi 2 of this times eta function times d phi, where eta has explicit expression like that. Okay. So this all about expression of Copeland shift function in the finite dimensional case. Now, the second step, so that means I need to reduce my problem into finite dimensional setting. So that means I need some kind of construction of Weil-Fornamen. For that, you observe that since I am working in a separable Hilbert space, so I can always give an existence of phi in this interval such that this is actually 1, 1. So in other words, if you consider this unitary operator, so that means actually I am rotating the spectrum of U naught little bit. In other words, actually I am considering this unitary operator. Okay. And then using Kelly transformation, you can give an existence of self-adjoint operator H naught, so that U prime is nothing but the Kelly transformation of this H naught. So if I have these things, then you can have an existence of self-adjoint operator H naught which satisfies this as well as this. Okay. So now once I have a notion of self-adjoint operator, then using Weil von Neumann construction like Voiculescu did for the
What if U0 has its spectrum on the whole disk?
You mean to say that whether this thing is invertible or not?
It may not be, by invertible you mean perhaps unbounded.
Unbounded.
Oh yes.
The inverse will be unbounded.
Right.
So you mean by invertible.
By invertible, that's why I said it's actually 1, 1, 1, 1. 1, 1, yes, I should not say invertible, it is 1, 1, yes. Okay. So this is, okay, this is the construction of Weil von Neumann. So that means, okay, Voiculescu and Sinha-Mahapato, they did for single vectors. So this is just similar kind of things with little modifications. You will be able to prove this kind of estimate, okay, for H naught and as well as U naught. Well, that's what I have written. The proof of this proposition is actually from this, follows from this lemma, actually Sinha and Mahapato paper with some little modifications. Well, so this is, now I need, so earlier if you notice, this is actually initial operator, U naught and H naught, okay. So, but U has this kind of expression, this is kind of to the IA U naught, so I have an estimate on the operator U naught, on U naught unitary operator. So now you need to have some kind of estimate, this kind of estimate on U as well. For that, what you have to do, since A is Hilbert-Smith, you actually don't care about the tail part. So given epsilon, you can have A suffix capital L, this is arbitrarily less than epsilon, and consider this G1, G2, GL and apply your earlier propositions. If you do that, perform this kind of calculations, then you will be able to get, this estimate. Okay? So therefore, in my earlier lemmas, actually we give an existence of finite rank projection which satisfies all those inequalities. Using that, if I compress my initial operator A, or the self-adjoint operator A, as well as this operator, you see I am compressed the operator in the space PH, and since P is finite rank, PH is finite dimensional. Okay. So that means if I define AP, U naught P and EP in this way, and this is as above, then you have all kind of estimate, you can get it. Just note one thing. So,
How do you know P0P still has, how do you know that operator is still invertible?
this operator?
When you compress H0, no, I plus PH0 goes to this third line.
This one?
Third line.
Oh.
How do you know that's still invertible?
Well, yes, this is self-adjoint, right? This is PH naught P, and this is I. So outside.
Oh, H naught was the
Self-adjoint operator.
Sorry,
Yes, yes.
It's the this is the inverse.
Yes. This
This
is
is the inverse. Yes.
okay. So look at here. So we have all the estimates in 2 norm, but sometimes I have to use trace. So instead of, so I cannot estimate this object in trace norm. So I have to use trace. So that means properties of trace is very important. Okay. So and to reduce my problem, I need this kind of estimate as well. Okay. Well, now if I combine all the information together, then you observe that since P commutes with these two operators, so therefore the object I have defined U naught P and UP, these are actually unitary operators on the space PH. So that means I give an existence of unitary operator in finite dimensional case. Okay? And not only that, you can have a sequence of projections Pn finite rank which satisfies all 2 norm goes to 0. That follows from my earlier lemmas. Okay, so now if I combine all kind of information, then this is the theorem we proved. So this is called the finite dimensional reduction of Copeland-Naidoo formula. In other words, okay, start with 2 unitary operators, different Hilbert-Smith, then you have the existence of A. Then if I consider this path S goes to the ISA, then if I calculate this trace, it's actually nothing but the limit of this object. Okay. Well, so once again, just go through a little bit of calculation. So what you do, you calculate this. I have an expression of this as well as this. Once again, you have big expression of summations. You just adjust it nicely. Then finally, you can have these 2 expression. Okay. Then individually you show that trace of this plus trace of this actually goes to 0, and that follows from the earlier lemmas. That means all kind of estimates. Okay, so that's what it is. So if this is the first term, if I take the absolute of this trace, it has this kind of estimate, this plus this, and all I have shown that goes to 0 as n approaches to infinity. This is for the first term. Similarly, for the second term, you have this kind of estimate. Look at here, I need this trace of this kind of things. So all term goes to 0. So this is also goes to 0. If I combine it, so therefore I have the lemma. Okay. So once I have, so now only the last part is remaining. So that means I have an explicit expression of Copeland-Naidoo formula for finite dimension. I reduce my problem. So only the last part I have to give an existence of shift function through some limiting procedure. Once again, we use similar kind of method like Gestesi, Pusnitsky and Simon, they used to prove Copeland trace formula for the self-adjoint case. Well, so this is the reduction theorem, and once I have in everything in finite dimension, I have an explicit expression of eta n, and just this is this little twist I need it. So from eta n, I just define eta 0 n, and I showed that this eta 0 n convergence in L1 norm. Okay. Well, so that means this is my final aim. I want to show that eta 0 n should be Cauchy in L1. For that, if I take any L infinity function, consider this kind of function and observe that ft times eta 0 n minus eta 0 m, it's actually flipped with f naught eta n minus eta n. If I take the absolute, this absolute same, and I have an expression of eta n and eta m, then I have to show that this is actually bounded by some L infinity norm f times some constant. Okay. Okay. For that, you just once again define a function g on the circle like this, and if I calculate this object, because I know eta n and eta m, f naught is there. If I calculate it, again do the integration by parts, you will end up with this kind of expression. So that means you have trace of this minus this plus this. Then what I will do, you just combine this minus this as well as this minus this. Okay. Now see, the way I have defined my function, this function actually lives each on circle. Okay. So therefore, if I perform double operator integral combining this and this, then I have the estimate in terms of the Pn part Apn or Pn u naught Pn part, something like that. Okay. So like this one. So that means if I calculate the absolute of trace, this is same as this is the trace properties. So therefore, I have the 2 norm of An as well as 2 norm of this. But this 2 norm I can have the estimation through double operator integral. So therefore, this is lesser equal to this one because this function is Lipschitz with this Lipschitz constant. Well, and this object goes to 0, we know, as n approaches to infinity using our original lemmas, old lemmas. Okay. Similarly, for the other term, you can show that this is goes to 0 as well as this is goes to 0. So therefore, finally, using Hahn-Banach theorem, L1 norm of this is nothing but sup of this with on the unit circle. Okay. And I already have an estimate of this is goes to 0 as nm approaches to infinity. So therefore, this eta 0 n actually converges in L1 norm. So therefore, I have the existence of eta function. And not only that, the way we have shown the existence of L1 function, using the same technique, you will be able to prove that L1 norm is actually bounded by A2 norm square. In fact, actually, if you start with eta 0 n, it is bounded by pi by 2 times Pn A Pn 2 norm, then it is bounded by A2 norm because Pn are projections. Well, so you can extend. So actually, I gave a proof for monomial, in fact polynomial, but you can extend this formula in this class. So that means this actually is psi double prime has absolutely convergent series. Okay, so these are the references. So this is actually series of paper of M.G. Crane in Russian. Of course, some of them I think translated to English as well later. Okay, so there actually he discussed all kind of means first order trace formula for both self-adjoint as well as unitary case. And this is the paper, Sinha and Mahapaତ୍ର, they actually extended Voiculescu's technique for unbounded case. This is for unitary case, and this is the original paper of Koplienko. This is the paper, again, Simon Gestesi, they actually gave an alternative proof, and this is once again another proof by myself and Sinha. And this Neidhart actually extended Koplienko formula for the unitary case, and this is the paper by Peller, where he actually kind of study this formula in the Bishop class. And this is the operator using double operator series. It is a famous paper by Birman and Solomia. And there, this paper, Potapov and Sukochev, they actually proved Koplienko trace formula or Koplienko-Neidhart formula for the linear path. And this is a series of paper by this once again Anna's group. So Anna, Skripka, Potapov and Sukochev. Actually, this is the paper that they solved the problem, Koplienko's conjecture, and later on they also investigated unitary operators. Not only that, also for contraction, they shown the what is called existence of shift function for any arbitrary order. So okay. So now, so whatever I have discussed actually dealt with a single self-adjoint operator. Then you perturb it, and then consider the Taylor remainder. Then what will be the formula, right? So that kind of problem I have discussed here. So now what I am doing with Professor Sinha is that instead of single self-adjoint operator, you start with a commuting self-adjoint operator. Let's say in the bounded case. So that means start with commuting self-adjoint operators, okay. Start with another commuting self-adjoint. I am in bounded operator setting, okay. So commuting bounded self-adjoint operator, commuting bounded self-adjoint operator. Assume that component-wise difference is Hilbert-Smith. Okay. Then we are looking for an expression of this object. For function phi, say from R2 to R, for nice function. Then consider this object. Well, with the hypothesis that means component-wise difference is Hilbert-Smith, for nice class of function, you will be able to show that this difference is trace class, no problem. Now, question is, okay, I am taking the trace, then what will be the right hand side? Well, first of all, why we consider this kind of expression? So one of the motivation is that Crane's trace formula you can think about as a mean value theorem. So now, if I want to extend this trace formula for the tuple, I need some kind of mean value theorem in higher order, right? So what is the corresponding mean value theorem in higher order. That is nothing but Stokes' theorem. So therefore, we are expecting to get an expression of this kind of formula like some Jacobian of phi c with some measure. That kind of, well, we are expecting, well, only the last part is remaining. Actually, once again, we use Weil-von Neumann-Berg's technique to reduce the problem in, once again, finite dimensional case. We need an expression in the finite dimensional case, and finally, we have to give an expression of this measure. What we have proved, or important observation, is that you will get only a measure here. Because we gave an example, this measure cannot be absolutely continuous with respect to Lebesgue measure on AB square. So only the last part is remaining. So we are expecting to have this kind of formula. So with this, I think I should stop. Thank you very much for your attention.
Ben, questions, comments? All right.
So I have a comment.
Yes.
I have a comment and a question. The comment is several times on your slide, and a script is mentioned. And her husband is my collaborator,
Yes.
Maxime
Maxime.
Zhukchenko.
Yes, yes.
Know that.
Right.
People who know Maxime.
Yes.
Secondly, Pella in his book has a Krein spectral shift formula for some class of phi's that is quote optimal. It's
Okay.
some very large class. Do you know of any in the analog for the Koplienko?
So you mean that first order case, Pillar has some
So Pella for the Krein case
grand case?
has results for some optimal class of functions.
Okay. Okay. No. Second order case, I think.
So I'm asking if you
Okay.
know
Okay.
of an
No. I do not know. So yeah, you are right. I also kind of gone through that paper. So that means first order case, some kind of maximal class is there. So second order, well, I do not know.
Anyone else? Comment or question?
Can you say anything about why a measure appears here in the example? Sorry.
Why?
The question is, if Arup could say more about the example which
Example.
produces
Okay.
a measure,
Well,
not a function.
for example, if you take, for example, one variable function. Okay. I think so. For example, so say let h1, h2 is equal to h, single operator. h1, 0, h2, 0 is equal to h naught. And consider a very simple case. So that means consider this function, say phi h minus phi h naught times psi h minus psi h naught. If you consider this kind of object, there you will be able to show that this measure and this measure is actually not absolutely continuous, right?
It's on the square, not on the, so there.
Yeah, on a line, yes.
It could wind up being on the diagonal or
Right.
something else. Because it's a square, it's probably some object that isn't arbitrarily bad, but there's no reason to assume that it's actually right.
Okay, if not, we have a break until 4:15, and let's thank the speaker again.